Okay, so this is equation for DCT. Let me start the slideshow. Okay, so if you look at equation of DCT, forward transformation kernel of DCT is identical to inverse transformation kernel HXY UV. And this transformation is given by alpha U into alpha V into cos of 2x plus 1 U pi by 2m into cos of 2y plus 1 V pi by 2n. And alpha u is given by root 1 upon m for u is equal to 0, and it is given as root 2 upon m for u other than 0. Okay, so from this equation it is clear that this discrete cosine transform is a real transform. Okay, so discrete cosine transform is real in nature. There are only cos terms and there is no sine term, means there is no j part. Okay, so it has only real part and no imaginary part. So DCT is real in nature, whereas discrete Fourier transform is complex in nature. So this is one difference with respect to DFT. DCT is real transform. Secondly, DCT's forward transformation kernel is exactly identical to inverse transformation kernel. So this is one more difference with respect to DFT. And as this is real transform, it needs very less number of computations as compared to DFT. And at the same time, it gives very good energy packing efficiency. And that's why DCT is very useful in image compression techniques. Okay, because of its simplicity, that is less number of computations, and at the same time superior energy packing efficiency makes it useful for image compression. Okay, so let us have a look in more detail to this transform, that is discrete cosine transform. So these are the important properties of DCT: same inverse and forward kernel, superior energy packing. It is simpler and it requires less number of computations than DFT. Okay, so let us see how the transform coefficient matrix looks like for DCT with n is equal to 2. Now n is equal to 2 means your input signal length is 2 or input vector length is 2. Okay, so your input vector will look like as shown here, fx is equal to f0 comma f1. Means there are only two samples, that's why n is 2. And second problem statement is determine DCT coefficients for n is equal to 4. So n is equal to 4 means your input vector length is 4. So as shown here, your fx is f0, f1, f2, f3. So let us have a look at first example, that is determining DCT coefficients when input signal length is 2. Okay, so here you can observe the DCT equation: forward transformation kernel alpha u alpha v into cos of 2x plus 1 u pi by 2m into cos of 2y plus 1 v pi by 2m. Now, when we are considering one dimensional signal, instead of gxy we simply need gxu, right? So gxu is given by these two terms, alpha u multiplied by cos of 2x plus 1 u pi by 2m, and this alpha v term won't be there. Alpha v and this term and alpha v term won't appear. Okay, so here for gxu is given simply by alpha u into cos of 2x plus 1 u pi by 2m. Okay, so very first coefficient, DCT coefficient C0, is given by alpha 0 into summation x runs from 0 to 1. Why x runs from 0 to 1? Because input signal length is 2. There are only two samples, F0 and F1. Okay. So in this summation, we have x runs from 0 to 1. F of x is our input vector into cos of 2x plus 1 u pi by 2n. Okay. Now here for when we are computing C0, it means u is equal to 0. So we substitute alpha u, we replace u by 0. Similarly, here we replace u by 0. So we get this equation as f of 0 into cos 0 plus f of 1 into cos 0, and alpha 0, if you look at the previous equation, alpha 0 is given by root 1 by 2. This is fixed for when u is 0. So alpha 0 is root of 1 by 2. This first term of this summation is f0 into cos 0. When x is 0, we simply get this as cos 0. Then when x is 1, here we get again as u is 0, here we again get in second term cos 0, f1 into cos 0. So the equation for very first DCT coefficient C0 is given by square root 1 by 2 f of 0 plus f of 1. We took this cos 0 is nothing but 1. So we get here simply f0 plus f1. So coefficient of f0 is root 1 by 2. Similarly, scaling factor of f1 is also root 1 by 2. Is this first step clear to all of you? Please type in the chat box how we have determined coefficient value C0. If you have any query, please type it in the chat box. Okay. Okay, so let us go to next coefficient. C1, next coefficient value C1 means u is 1. So in this equation and here you have to substitute u as 1. So here it becomes alpha 1 summation x runs from 0 to 1 fx cos of 2x plus 1. In place of u, we are writing 1 into pi divided by 2n, that is 2 into 2. We get here as 4. Okay. So now as per previous equation, alpha 1 is given by square root of 2 by n. Now in our example, n is 2, so it becomes square root of 2 by 2. Okay. Then this first term, there are two product terms, f0 into cos pi by 4 plus f1 into cos 3 pi by 4. Why we get here pi by 4? Because here x is 0. So if we substitute x here at 0, we get this term as pi by 4. And here why we get 3 pi by 4? Because for second term x is 1. So 2 into 1 plus 1, that is 3. 3 into 1, that is 3. 3 pi by 4. That's why we are getting here cos 3 pi by 4. Okay. So here finally ultimately this results in value 1. Okay. So here we get f0 into cos pi by 4 plus f1 into cos 3 pi by 4. Now what is value of cos pi by 4? Cos pi by 4 is root 1 by 2. So here we get square root 1 by 2 into f0. And what is value of cos 3 pi by 4? It is minus root 1 by 2. So we get here minus root 1 by 2 into f1. So here scaling factor for f0 is root 1 by 2, and that for f1 is minus root 1 by 2. Okay. So here we effectively have four coefficients. For n is equal to 2, our x varies from 0 to 1. Okay. And y varies from, sorry, not y, u also varies from 0 to 1. Okay. So this is your variation in x. X can take value as 0 and 1, and u can take value as 0 or 1. Okay. So for when u is 0, there are two samples x0, x1. Corresponding to that, we have two values f0, f1, and scaling factor for f0 as well as f1 is root 1 by 2. So here we will get root 1 by 2, root 1 by 2. Okay. Then when your u is 1, we are getting this term. So here coefficient for f0 is root 1 by 2, and coefficient of f1 is minus root 1 by 2, and this root 1 by 2 is common to all these four terms, so it is taken outside of the coefficient matrix. So finally, when n is equal to 2, we get DCT2, that is coefficient matrix for DCT as square root of 1 by 2 into bracket 1, 1, 1 minus 1. Okay, so this is your DCT coefficient matrix for n is equal to 2. Okay, so hope this step is clear to you. Okay. Okay, let me erase the board. Okay. Okay, so this is DCT coefficient matrix for n is equal to 2. Now on similar lines, we can compute DCT coefficient matrix for n is equal to 4. Now what are the changes? When your n is 4, it means your input signal has 4 samples, F0, F1, F2 and F3. So you need in this forward transformation kernel, alpha u into 2x plus 1 u pi by 2m, you need to vary u from 0 to 3, and you need to vary for every u value, you need to vary x from 0 to 3. So try to compute this forward transformation matrix when n is equal to 4. So you can directly use this forward transformation kernel alpha u into cos of 2x plus 1 u pi by 2m, and in this forward transformation kernel, for every value of u, substitute x at 0, 1, 2, 3, so that you get first row of transform coefficient matrix. Okay. Similarly, when u is 1, again for u1 substitute x at 0, 1, 2, 3. With this, you will get second row of your DCT transform coefficient matrix. So now I request all of you to compute first row and second row for DCT matrix with n is equal to 4. Okay. So on similar lines, we can compute DCT coefficient matrix when n is equal to 4. Okay, so your second term will be a, b minus a, where 1/2 is taken common from all these elements, and remaining part, that is a, is nothing but root 2 cos of pi by 8, that is 1.306, and b is nothing but b is equal to root 2 cos 3 pi by 8, and answer is 0.541. Here please note down that 1/2 factor is taken out as common to all these elements. Okay, so here, like for n is equal to 2, we varied x in this direction, u in this direction. Similarly, when n is 4, here we are considering x in this direction. X is 0, 1, 2 and 3. And here u value, this u is 0 for very first row, it is 1 for second row, 2 for third row, and 3 for last row. So your u is varying in this vertical direction and x is varying in this horizontal direction. So when u is 0, we can compute forward transformation kernel value for x is equal to 0, 1, 2 and 3. So all these values are 1/2, 1/2, 1/2, 1/2, and this 1/2 is taken outside from this 4 elements. Similarly, when we take u is equal to 1, again we vary x at 0, 1, 2, 3. Accordingly, we substitute these values in the forward transformation kernel, and we get these values a, b minus a, where again 1/2 is common to all these 4 elements. When u is 2, again we vary x from 0 to 3 so that we get these 4 terms. 1 half minus 1 half minus 1 half 1 half. And when we take 1 half outside, we get this as 1 minus 1 minus 1 1. And when u is 3, we get last row, which is b minus a minus b. And again, 1 half is common to all these terms. Okay. So this is our forward transformation matrix for n is equal to 4. Similarly, if n is 8, you can get 8 by 8 DCT coefficient matrix. Okay. Now, using this matrix, we can easily compute discrete cosine transform of a given signal simply by matrix multiplication method. So let us have a look at few numericals based on DCT. Now, before going to numericals, let us understand how we can represent this DCT coefficient matrix in different format. Okay, so this is one representation of discrete cosine transform coefficient matrix. This equation is another representation. So, okay, so these are various representations of your forward transformation kernel. In equation form, we can represent gxu as alpha u into cos of 2x plus 1 u pi by 2m. In matrix form, we can represent the kernel with this particular matrix, okay, 4C or DCT matrix for n is equal to 4. Now, the same thing we can also represent graphically, okay, and when we represent it graphically, usually it is known as basis functions, okay. So basically this alpha u into cos of 2x plus 1 u pi by 2m, this is forward transformation kernel which represents basis functions for discrete cosine transform. Okay, so these are various names to the same thing, and these are various forms of the same thing, that is DCT coefficient matrix or DCT kernel or DCT basis functions. Now, when we plot it graphically, it looks as shown here. These are basis functions for DCT when n is equal to 4. So as shown in previous slide here, this u varies along vertical direction 0, 1, 2, 3. And for every value of u, we get variation of x from 0 to 3. And accordingly, we get here 4 coefficient values. So the same thing is represented here as a graph. So for u is equal to 0, all these all these coefficient values are identical to each other and its value is 1. Okay. So again, we are not considering this common factor 1 half. We are plotting the basis function using these values. Okay. So here all these values are 1. Okay. When u is 1, we get the value as a, b minus a. So here this is your a, which is 1.306. B is 0.54. Minus b is minus 0.54. Minus a is minus 1.306. So these are basis functions when u is equal to 1. Then next basis function when u is equal to 2, it is 1 minus 1 minus 1 1. So we can plot it as 1 minus 1 minus 1 1. And last row, that is b minus a minus b. So the same thing is shown here. B is 0.54, minus a is minus 1.306, then plus a, that is 1.306, and then minus b, that is minus 0.54. Okay, so these are basis functions for discrete cosine transform, and looking at these basis functions, we can easily say that it has cosine nature. If you try to draw a continuous signal through these discrete samples, you will get a cosine wave. Okay, cosinusoidal wave. Okay, so these are basis functions for DCT, and this is your DCT in matrix form, and this is your DCT kernel in equation form. So all of them represent the same thing, only difference is its representation is different. It is here it is represented in mathematical equation. Here it is represented as matrix of coefficient values, and here it is represented as graph. Okay, as cosine waves. And we can say that basically when we take discrete cosine transform of input signal, what we do is we take weighted addition of samples, and these weights are proportional to cosine signal, right? This is your x0, x1, x2, x3. These are your input samples. And for every DCT coefficient values, we are weighting input samples by cosine wave, or with weights which are proportional to cosine signal. And for very first coefficient, this cosine frequency is always 0. Why? Because all of them are identical, means it is a constant value or it is equivalent to DC signal. So for very first signal, frequency is always 0. And as we go to next and next basis functions, frequency goes on increasing. Okay, so here frequency is as shown here, it is doubled, then it is here it becomes 4 times. Okay, so your very first coefficient for DCT is always it is equivalent to average of all samples, or it is a coefficient with 0 frequency. And as your u value increases, frequency increases. And same was true for your Fourier transform, because in case of Fourier transform also, now we have weighted addition of sines and cosine terms. Please listen to the prayer.